professor in Instituto Superior Técnico, is maybe the major engineering university in Lisbon, Portugal. And today I will be talking about numerical analysis that we perform using a 3D model for crack growth and plastic wake to predict the fatigue crack closure. This work was performed by master student Carlos Esteves, by Professor Baptista, myself, Infante, Daniel Braga, Farahani, and Moreira from Inês. Okay, we decided to divide the presentation in 5 main topics. I will start with a brief introduction, after materials and methods, then defined element analysis model, the results that we obtained, the strength field, crack closure, plastic wake, plastic zone size analysis, stress intensity factor, and finally I will conclude the presentation. Not this one, sorry. Okay, in terms of the introduction, as you know, we can predict the crack tip stress and strain field determination using numerical and experimental approach. In this study, we use a numerical approach. Both elastic and plastic solution can be achieved, and using defined element analysis, we can predict the stress intensity factors, the T stresses, or the plasticity induced crack closure. In this study, we use these both, the stress intensity factor and the plasticity induced crack closure. The main goal of the study, it was to determine the plastic crack from behavior using defined element analysis. In this case, it was the ABAX program. In terms of the specimen that we simulate, it was this one. The experimental tests performed by Inês, and it was presented by Dr. Bezat in other section, but we use the same geometry of the specimens. The specimens have this configuration with a notch in the middle with 16 millimeters. After this, we perform fatigue tests to obtain established crack propagation, and for the simulations, we use the dimension of the left side, namely 21 for the specimen MT2, that I will show you the results, and 26.9 for the specimen MT4. We use these mechanical properties for the material because the material is aluminum alloy 6082 T6, and we use the linear kinematic hardening model to predict the elastic deformation and the plastic deformation. No, sorry. For the finite element analysis, we decide to use the methodology not release, and in each time step, one node of the crack front is released, as you can see in the image. Only one load cycle per time step, and we simulate several fatigue cycles in each time step. In terms of boundary conditions, we consider only 1/8 of the specimen was simulated because we have symmetry in this kind of specimens. We applied 10 kilonewtons with a stress ratio of 0.1 in each time step. We perform convergence mesh analysis, and we define the number of elements equal to 120 because we obtain established values for both for the specimen MT2 and for the specimen MT4. In terms of the node release methodology, we use 2 different approaches. In the first cycles, the nodes are released at maximum load to obtain the plastic wake, and in the last time step, we apply an unloading and unloading to obtain the crack closure and the crack opening. In terms of the results for the stress field concerning the MT2 specimen, we use, as I said before, a crack length equal to 21 millimeters. We have the stress intensity factor equal to, for more or less, to 350 megapascals square root of millimeter, and we obtain the plastic radius of 0.747 millimeters. And when we apply 30% of this value and 90% of this value and 60% of this value, we can see that the plastic weight will increase with the percentage of the plastic radius as expected. We perform the same analysis for the MT4, and of course the plastic weight increase because the initial crack length is higher compared with the specimen MT2. For the crack closure, we use two different approaches. The tip stress, where the stress sign changes when the crack opens or closes, as you can see here, and we can observe that the crack is open in this part and closed in the other one. And we use another approach, the crack displacement, where the first node of the crack front displacement increases, and we obtain something like this. In terms of results, comparing both approaches, we can see that for the tip stress, the closure is always higher values compared with the open, but for the crack displacement, the results for close and open is more or less the same, but we observe difference when we compare the surface results with the mid-plane results, and the explanation is in the surface we have plane stress, in the middle plane we have plane strain. In terms of the plastic weight, and I will show you only for the specimen MT2, because for MT4 is more or less the same results, we decide to obtain results for 5%, 50%, 30%, 60% and 90% of the plastic size, and we can conclude for 5, 50, 30% of the plastic size, the results are very bad, you can see here, but for 60 and 90 are more or less the same. The same for MT4. And right now for the plastic zone size analysis, we use two different theoretical expressions. The first one, Degdale, and the second one, Kojavisky. And we look for two different types of things. The first one, the crack extension, as you can see here. And the other one is the maximum size that we can see here in the image. For the maximum size, we can see that the plastic weight increase, but is almost the same. But for the crack extension, we can see that the results are different and increase, of course, with the plastic weight. Another conclusion is the Dugdale methodology presents always higher values comparing with the simulations, but the Kojavisky, the results are above the numerical results that we obtain. In terms of the stress intensity factor analysis, we compare our results, the numerical results, with the theoretical over the deterministic stress intensity factor calculation algorithm that is presented in the standard ISTM. And if you look, the results are very, very similar, with a difference of 0.84% and 0.97%. Concluding, The 3D elastic plastic models for the empty specimens are developed with different mesh densities and plastic weights around the crack tip. We use different mesh densities to observe and to extrapolate the results for the crack opening and closure loads. The crack tip stress criterion predicts higher crack closure loads. We observe different values for the specimen in the mid-plane comparing with the surface, as I showed you before, and for the simulating a plastic weight of about 60% of the plastic's size, we obtain results with quality comparing with percentage less than this value. The 3 simulation allowed for accurate plastic zone shape and size determination, and finally the stress field allowed for accurate stress intensity factor determination using the over-deterministic algorithm. And that's all for this presentation. Thank you for your attention.
Thank you very much. So, yes.
Okay, and the plastic zones, can you show the slides with the comparison with Dardel and Kujavsky? One is at the left graph and right graph. It's at the beginning and at the end of simulation.
Yeah.
And so the plastic zone is getting smaller because of crack closures.
Yeah, that's right.
And the values of Dardel and Kujavsky are for plane strain or plane stress or which?
I'm not sure, but I think it was plane strain. Okay, because we consider in the middle of the section, not in the surface. Yeah.
And the crack front was...
Of course, we have the results for both, but this graph...
Yes. The crack front was straight?
Yeah,
or
it was straight. That is a good question because the experimental part are measuring the crack front. Okay, but here we consider for the simulations established one with the same value in all the front of the crack. Yeah.
So, if no other question, I have the specimen thickness. Maybe I missed the thickness.
The thickness I can show you here, but it was 3 millimeters.
Yes, 3 millimeters.
Yeah.
Okay. And the load ratio in the simulation?
0.1.
0.1.
Was not. This point is 0.1. Okay. 0.1 stress ratio. We apply always 10 kilonewtons, the maximum load that it was applied in the experimental tests, and for the simulations, 0.1.
Yes.
Thanks for your presentation. Did you observe some ratcheting effects, local ratcheting effects, close to your crack tip because your hardening looks really soft?
That's right, and this is the explanation why. I know that is not your question, but we use this model. This is a quasi-static model, not a dynamic model, and the explanation is because we have a very small amount of the cyclic hardening, but no, we did not perform this kind of simulations. Yeah. Maybe later. In this moment we are in the end of the research project because this project it was financed by the Foundation, Science Foundation in Portugal, but maybe a next one. Okay.
So, once again, thank you very much.